So, hello everyone. Uh, I'm Gitanjali. I'm a PhD student from IIT Delhi. So, I welcome you to the eighth live section of the quantum mechanics course. So, in this section, I will solve some of the problems that will help you to understand the assignment, and that will also help you to understand the concepts of the quantum mechanics problems. So before starting solving the problems, let me go through the concept that we have seen in this week. So in this week, we study about harmonic oscillator and one of the different method to solve the Hamiltonian of harmonic oscillator using the ladder operator. So for harmonic oscillator, you know that the Hamiltonian is given by this equation h equal to p square by 2m plus half m omega square x square. So to solve this Hamiltonian, uh, what we have done is we have introduced ladder operator. So ladder operator can be of two types. One is annihilation operator and other one is the raising operator. Annihilation operator is it is represented by A and raising operator is represented by A dagger. So by using these ladder operators, what we have done is we have expressed the position and momentum operator of this Hamiltonian. So for the position operator can be represented by this ladder operator using this equation, and for momentum it is represented by this equation. So these equations are introduced in such a way that the Hamiltonian that we have known so far, that is xp equal to ih cut, is remain unchanged. So to keep this commutation relation unchanged, we have introduced the ladder operator representation of x and p in this way. So now using this two equation, you can solve for the raising operator, how it can be expressed in terms of position and momentum representation, and the lowering operator in terms of position and momentum representation, which is given by this equation. So now if you take these two expression one and expression two, then what you see is the commutation relation is now given by this form. A dagger is equal to 1. And after introducing the ladder operator, now if you take the eigenstate of this harmonic oscillator potential as n, then what this ladder operator do is, when you act this lowering operator on this eigenstate, then it lowers the eigenstate of the system. Like from n, it takes the state n to a state n minus 1, which is given by this expression. So with a coefficient root over of n. Now, in contrast to this uh, lowering operator, we have another operator, that is raising operator. What it does is it takes the state n to n plus 1. So when you act a raising operator on any kind of state n, then it raises the uh, eigenfunction of this system to the next higher energy state with a coefficient root over of n plus 1. So these are the expression of how the action of lowering and raising operator changes the state of the system. By using this equation also, in addition to this raising and lowering operator, we introduce another type of operator, which is number operator n. And this number operator n is expressed as multiplication of this ladder operator and is given by A dagger A. Okay, so this now use this expression for A dagger and A. Then you can find out that the n can be represented by this equation 3, which is n equal to h by omega h cot minus half. So now if you rearrange the whole equation, then in what you see is the Hamiltonian is now written in terms of this ladder operator as this expression, which is h cot omega a dagger a plus half. Now a dagger is nothing but the number operator. So the Hamiltonian is h cot omega n plus half. Now to know how this number operator acts on any kind of eigenstate, what you can do is, you know that when Hamiltonian acts on any kind of state n, then it gives the energy eigenvalue with the same state n. Now the expression for En, you know, it is n plus half h cot omega, and in the left hand side, what you can do, you can put this is expression omega h cot n plus half. So now if you compare the left hand side and right hand side, what you can see is the action of number operator doesn't change the state of the system. It only uh, gives the eigenvalue of n, and it keep the eigenstate unchanged. So that means the number operator is a eigenstate of a state n with eigenvalue n. So here you see the n is nothing but a dagger a. So when a dagger a acts on a system, when it acts on a eigenstate n, then it doesn't change the state of the system, and it gives the eigenvalue of n. Now, in addition to this, you also study about the Heisenberg equation of motion for the position and momentum operator. So, by using the Heisenberg equation that we have seen in one of the previous section, you can find out the how this ladder operator changes with respect to time. So, this ladder operator changes. Let's say for lowering operator, it changes according to this equation, which is given by at equal to a0 e to power minus I omega t. Now, for the raising operator, it changes, it evolves in time in this manner, which is given by a dagger 0 e to power I omega t. So by using this, the expression for lowering and raising operator, you can easily find out how this position and momentum of this any particle changes with respect to time. So now if you work out the total expression, if you put the expression for lowering and raising operator, then what you can see is the position representation is given by this equation. This is how the position of the particle changes with respect to time, and the second is how the momentum of this particle changes with respect to time. So by using this concept, you can easily find out how the state of the system changes with respect to time, what will be the state of the system after some time t, as well as you can easily find out how the state will evolve with respect to time. Okay, so let me start solving some of the problems related to this concept. So the first problem, let us see the first problem. So it is about the, it tells that the ground state wave function of a linear harmonic oscillator is given by this. So it is given to you the ground state wave function, which is nothing but a exponential minus m omega x square by 2h cut. So here A is a constant, and it is telling that using raising and lowering operator, obtain the wave function of the first excited state of the harmonic oscillator. So it is asking about what will be the position representation in the first excited state when you given the ground state wave function. So to get the expression for the higher state, what you can do is you use the raising operator. So the raising operator will, let's say this is the ground state and this is the first excited state. So when you act and the wave function in this state is, let's say psi0x, which is given to you, and the wave function in this first excited state is psi1x. So now when you active, you use the raising operator A dagger, it will raise the state of the system. It will um, change the state from ground state to first excited state. So that means you need to find out, you need to use the raising operator and find out what is the expression for the first excited state. So this can be written as psi1 x equal to A dagger psi0 x. Okay, so this you have to solve. Now A dagger, you know, A dagger as I have shown in the introductory part, A dagger is it is expressed in terms of the position and momentum representation as root over of m omega by 2h cut x minus ip by root over of 2m omega h cut. This is the expression for the raising operator. So now what you have to do, you have to just use this expression and put it in this equation. So psi1x will be root over of m omega. I think this color is not visible. Let me rewrite. So psi1x equal to root over of m omega by 2h cut x cap minus ip by 2 omega h cut psi0 x. So now use the position representation of momentum operator, which is nothing but P equal to minus IH cut dou by dou x, right? That means this will be equal to root over of m omega 2h cut x cap. There will be h cut here. Root over of 2m omega h cut k d by dx I0 x. Now you have to just solve this equation to get the first eigenstate. The I0, sorry, we are finding out the psi1x. Psi1x equal to root over of m omega by 2h cut x and a times the position representation in the ground state, which is a exponential this. So a exponential minus m omega x square by 2h cut, and the other term is minus H cut 2 m omega H cut omega d by dx of exponential minus m omega x square by 2h cut. So this, this will be exponential, the term that is given here, this will be same. So that means this is root over of m omega 2h cut x a exponential 2h cut minus, so this will be plus m omega x exponential minus m omega x square by 2h cut, right? So these two terms are same. That means you will get 2 times m omega by 2h cut x a exponential minus m omega x square by 2h cut. So that means the final is a root over of 2 m omega h cut, and this is psi 0. So this is the expression for the position representation of the first excited state. This is how you can calculate the position representation in any state n if you are given the ground state. So if ground state is given, then by using the raising operator expression, you can easily find out what is the expression for the position representation of higher excited state. So in this problem, I have calculated it for the first excited state, and for second excited state, what you can do, I can give a clue. Second excited state, what you have to do, you have to act the raising operator twice on the ground state, so that it can take from ground state to the second excited state. Okay, so this is how you can calculate the position representation. So let me move to the next problem. So the next problem is based on the probability. So it is asking about the probability of finding the particle in the non-classical region. So what is given? It is given that the wave function of the ground state of a harmonic oscillator of force constant k and mass m is given by psi 0x equal to alpha by pi 1 by 4 8 bar minus alpha x square by 2, where alpha equal to m omega 0 by h cut and omega 0 square equal to k by m. So this is given, and it is asking what is the probability of finding the particle outside the classical region. Okay, so outside the classical region means the energy of the particle will be less than the potential energy. And for the ground state, the energy is nothing but h cut m omega 0 h got omega 0 by 2, which will be less than v of x, which is half m omega 0 square x square. So that means the square must be greater than h got by m omega 0, right? So this is nothing but 1 by alpha. Alpha is given here. This is 1 by alpha. So from here you can easily find out what is the limit of this non-classical region. So that means the x will be, the non-classical region limit will be x greater than 1 by alpha and x less than minus 1 by root over of alpha. So these are the limits for the non-classical region. So to find out the probability, what you can do, use the postulates of quantum mechanics. Probability will be psi 0 square dx, right, for 1D. And the limit will be the non-classical region. Here there are two limits. One is greater than minus 1, greater than 1 by alpha. Other one is less than minus 1 by root over of alpha. There is a root here. That means this will be 1 by root over of alpha to infinity psi 0 x square dx. The other one is, it will be from minus infinity to minus 1 by root over of alpha psi 0 x square dx. Psi 0 is given to you, so you can easily find out what is the expression for psi 0 x square. So this is nothing but the product of complex conjugate with the wave function that is given to you, and this will be alpha by pi half 8 bar minus alpha x square. So now you have to just put this psi 0 expression in this limit. That means the probability will be 1 by root over of alpha to infinity. This is by pi and 8 bar minus alpha x square dx plus minus infinity to minus 1 by root over of alpha psi 0 x square. Psi 0 of x, which is this. And you can see this e to power minus alpha x square is an even function, right? So that means this limit, these two limits would give same value. So now we can reduce the expression. It will be 2 times of root over pi by alpha 1 by infinity e to power minus alpha square dx. Now what you have to do is you just have to make the substitution. This limit is already given. This will be given to you 1 to infinity e to y minus y square dy will be 0.14. It is approximately equal to 0.14. So now you need to express this whole integral in terms of this. So for that you can make a substitution like alpha x square equal to, you can take it as y square. Now if you do it, then you will get 2 times of 1 to infinity e to power minus y square dy. There will be a root over of pi here. So that means this will be equal to 0.14 by root over of pi into 2. So what you will get is you will get a value which is approximately equal to 0.16. So that means the probability of absorbing this particle in the non-classical region is 16%. Okay. So this is how you can calculate the probability of a particle in a non-classical region. Now let me move to the next question. This is the second question we've solved. This is the third question. So in this question, let me read out the question for you. So it is given in the harmonic oscillator problem, the creation and the annihilation operator in the dimensionless units are defined by this expression. So in a dimensionless unit, the A dagger can be written as x minus ip by root over 2, and the annihilation operator can be represented as x. So in the third question, it is given in the harmonic oscillator problem, the creation and annihilation operator in the dimensional units are defined by A equal to x minus ip by root over 2, and the annihilation operator is x plus ip by root 2. This is given to you. Now it is also given the unnormalized energy eigenfunction of a state psi n. So psi n is given 2x square minus 1 exponential minus x square by 2. Now it is asking what is the state of this system. So in which the quantums, if you are given this three expression, then you need to find out what is the state of the system, like what is the quantum state of the system. And also find the eigenfunction corresponding to this adjacent states. So first you need to find out what is the state n, right? Now in the introductory part, I told you that if the number operator n, if it acts on a state n, then what we will get is you will get an eigenvalue n with the same eigenstate. So that means if you act this number operator, then you can easily find out what is the quantum state of the system, which is n here, right? So A dagger and A is given to you. So let us see what is the expression for A dagger A in this dimensionless unit. So it will be 1 by 2 x minus ip and x plus ip. So that means then you need to put the position representation of this momentum operator, because the wave function is given in terms of position representation. So this is nothing but it will be p is minus ih square dou by dou x. So you need to put this expression here and here. So it will become A dagger A will be x minus d by dx and x plus d by d. So this is the expression for A dagger A. Now what you have to do is You have to just solve this equation and find out what is the value of n. This sin is a dagger is half x minus d by dx and x plus d by dx. The expression for sin of x is already given, which is this. So this will be 2x square minus 1 exponential minus x square by 2. Now you just need to solve this differential operator. Okay. So what you can do, just first find out what is this value. This will be x plus d by dx with 2x square minus 1 exponential minus x square by 2. That means it will be x 2x square minus 1 exponential minus x square by 2 plus d by dx of 2x square minus 1 exponential minus x square by 2. So this will remain unchanged, the first term. The second term, what you will get is 4x exponential minus x square by 2. And the other one is plus 2x square minus 1 derivative of exponential x square by 2. So it will be minus x exponential minus x square by 2. Right? So now if you see these two terms, first and third, they are equal and one is opposite. One have opposite sign to the first one. This 1, 3 term will cancel. So what you left with is the second term, which is 4x exponential minus x square by 2. Right? This is the value for this one. Now we have to apply this operator to this, the final value. So let us calculate. So a dagger a sin x equal to half x minus d by dx 4x exponential minus x square by 2. So that means it will be 2, the 4, 2, and this one will be x square exponential minus x square by 2 minus d by dx of x exponential minus x square by 2. Now if we solve it, we will get sin x equal to 2 times x square exponential x square by 2 minus exponential minus x square by 2. The third term is plus x square exponential minus x square by 2. So these two terms, you have to just solve this one. Okay. So that means it is 2 times 2x square minus 1 exponential minus x square by 2. So this is nothing but the state that is given to you, sin x. So what we got is a dagger a equal to a dagger a sin x equal to 2 times of sin x. A dagger is nothing but n. So n acting on a eigenfunction gives 2 times of that eigenfunction. So that means if you compare it to this expression, if you compare it, that you will get n equal to 2, right? So that means the quantum state of the system n is n and it is 2, right? So now you got the value for the first problem. So here you got n equal to 2. Now in the second problem, it is asking about find the eigenfunction corresponding to the adjacent state. So now you got n equal to 2. So the adjacent state for n equal to 2 is nothing but n equal to 1 and n equal to 3, right? And how can you get the expression for n equal to 1 and n equal to 3? So for 2 to 1, n equal to 2 to 1, you have to use the lowering operator a, right? So if you put the lowering operator a, you can easily find out what is the expression for the state n equal to 1. So this is 1 by root 2 worked a on 2. 1 by root 2 is the normalization factor. So 2 is given. 2 is nothing but n equal to 2x. Now you have to put the expression for a. A is given. The problem a is given. This one. Similar to the a dagger, you have to put the position representation of p and you need to find out what is the expression for the lowering operator in position representation. So this will be nothing but x plus dy dx. Okay. So that means here it is x plus d by dx psi 2x, which is given to you 2x square minus 1 exponential minus x square by 2. So this you can easily solve. So let me solve it quickly. This will remain unchanged, and this one is d by dx of 2x square minus 1 exponential minus x square by 2. So what you will get is, so this total expression, if you solve it, you will get around 4x exponential minus x square by 2. So that means it will be 2x exponential minus x square by 2. So this is the expression for the state n equal to 1. Now to go from n equal to 2 to n equal to 3. So what you need the raising operator A dagger, right? So now the expression for psi n equal to 3x will be 1 by root 3 A dagger 2. This will be 1 by root 3. A dagger is x minus d by dx. There is also 1 by root 2 here. And 2 is 2x square minus 1 exponential minus x square by 2. Right? So now you have to solve this one. It is root over of 6. Then the x term will remain unchanged. And this is d by dx. 2x square minus 1 exponential minus x square by 2. Now solve this operator, solve this differential, and you will get psi n equal to 3x equal to 1 by root over of 6 4x cube minus 6x exponential minus x square by 2. So this is the expression for the n equal to 3 state. This is the answer. So this is how you can calculate the expression for a higher and lower state by using the raising and lowering operator. And if you want to calculate the quantum state of the system, like the quantum number related to this quantum state, then what you can do is you can act the number operator, because number operator is an eigenvalue of the state n. So if you act this number operator, then what you will get is the eigenvalue n and the same eigenstate n. So let us go to the next problem. Let's go through the question once. So it is given an electron is confined in the ground state of a one-dimensional harmonic oscillator such that root over of expectation of x minus x square equal to 10 to the minus 10 meter. So this is given to you. Now it is asking find the energy in electron volt required to excite the electron to its second excited state. So in a harmonic oscillator, if you represent this energy eigenlevel, so this is the ground state, this is the first excited state, and this is the second excited state. And the energy required to excite one electron from here to the second excited will be the energy difference, right? Del equal to E2 minus E0. So E2 is 2 plus half h cot omega, and E0 is half h cot omega. So that means delta is 2 times of h cot omega. Okay. So the energy required to excite to the second excited state is 2 times of h squared omega. H squared you know in electron volt, but you don't know the omega term. Now, and it is in the question it is asking about find the energy required in electron volt to excite this electron to the second excited state. Now, according to the virial theorem, you know that the expectation of the kinetic energy in a state n is equal to the expectation of potential energy in state n. Right? Now, if I need to if I calculate the expectation of Hamiltonian operator, then it will be T plus V, and it will be nothing but 2 times of V, right? Now, for the ground state, initially the particle was in the ground state. So that means if you put the ground state expectation value, so when the particle is in the ground state, then what will be the expectation value of its energy? It will be the energy of the ground state, which is h squared omega by 2. Now in the right hand side, just put the expression for potential energy, which is half omega square x square. M omega square is a constant, so you can take it out from the expectation value. So that means the x square expectation value will be equal to h squared by 2m omega, right? Now, if you want to calculate what will be the expression, what will be the value of omega, then the omega will be nothing but h squared by 2m x square expectation. This is by using this expression you can calculate what is the value of omega. Now it is what is given to you? It is given to is x minus x square equal to 10 to the power minus 10 meter. And this is nothing but I think you already know what is the expression for this one. So let me write it clearly. This is given to you x minus square. So now you can write it as x square plus expectation of x square minus 2 times of x. You can write it as this, right? Now if we solve it, it will be x square expectation plus expectation of x square minus 2 times of expectation of x square. So that means this is equal to x square expectation minus expectation of x square. Now for harmonic oscillator, the expectation of x will be equal to 0 because x is, if you write it in terms of a and dagger, it is approximately equal to a plus a dagger, right? If you want to find out the expectation of x, then you have to solve this equation, right? So this is nothing but a plus a dagger on n. Now if a acts on n, then it will changes the state of the system. So it will take the state from n to n minus 1. So this will be root over of n minus 1. The other one is a dagger. So it will take the state from n to n plus 1. So it will be root over of n plus 1, n plus 1, right? Now if you take the inner product of n with n minus 1 or with n plus 1, it will be 0. So that means for harmonic oscillator, the expectation of x is 0. So that means this one is nothing but it will be equal to root over of x square. This one is 0. So it is given, this one is equal to 10 to the power minus 10 meter. So this will be, so for omega, what you need to find out? 2m x square, right? So this will be equal to h squared by 2m 10 to the power minus 10 square. This is the expression for omega. Now, to calculate the energy required to excite the state from ground state to the second excited state, delta is 2 times h squared omega, right? So now you need to put the expression for h and omega and the values, okay? 2m x square, this is h squared square, m. What you can do is, it is given the particle is an electron, and you know the rest mass of electron will be mc square, which is nothing but 0.511 mega electron volt. So use this one. For that you need to multiply c square in both numerator and denominator. Now if you put the value of h cut value in electron volt is nothing but 6.58 into 10 to the power minus 16 electron volt second. C, you know, it is 3 into 10 to the power 8 meter per second. mc square is 0.511 into 10 to the power 6 electron volt, and x square you have just seen, it is nothing but 10 to the power minus 20. Now if you put these values in this expression, then you will see that delta E will come around 7.62 electron volt. So this amount of energy will be required to excite the particle from ground state to the first excited to the second excited state. Okay. Up to now, I think everything is clear to you. If you have any doubt, then you can ask me. Okay, let us see the next problem. So the next problem is, it is based on the spin quantum number. So it is telling the component along an arbitrary direction n cap with direction cosine nx and y and z of the spin of a spin up particle is measured. So, and it is asking what will be the result of this. The question is that for a spin-off particle, we measure the arbitrary direction and k. So instead of x, y, and z direction, so we measure in a different direction, which is nx, ny, and z direction. Now it is asking what will be the result of this experiment. So the result will be nothing but the eigenvalue according to the postulate. So you need to find out the eigenvalue in this question. So for spin-up particle, you know that the spin quantum number S is given in terms of the Pauli matrix sigma. So that means Xx will be h code by 2 sigma x h code by 2. Sigma x is 0, 1, 1, 0. Depend 1 minute. Screen is not visible. So presenting 1 minute. So where is my screen? One minute. There is a connectivity issue in my tab. So please wait for 2 minutes. Let me rejoin the yes, uh, there is a problem in my tab. So let me share my screen in laptop for now. No connecting. So now if you see, uh, oh, this problem is also solved. Okay. So this was the problem we were solving. So now if you see the spin angular momentum can be expressed in terms of the Pauli matrix sigma x, sigma y, and sigma z. So this is x. If you want to find out the representation for the x component of spin angular momentum, then it will be x is equal to it will be given by this expression. This matrix element and Sy will be h cot by 2 0 minus I 1 0 and Sz will be h cot by 2 1 0 0 minus 1. Now n is given n equal to nx I cap, ny j cap and nz k cap, right? So and S is xx I cap, sy z cap and sz k cap. Now, if you now it is in the question it was telling that you measured the spin angular momentum in n direction. So that means you take the measurement which is n dot s, right? So n dot s is nothing but nx uh, nx sx and y sy and nz sz. Now, if you put the matrix element of xx, xy, and sz, what you will get is this expression and uh, so let me walk it up 1 minute. So now if you put the matrix element for xx, xy, xz in the n dot s term, then you will get the final expression is final matrix element is this, which is nz h cot by 2. The second one is nx h cot by 2 minus I ny h cot by 2. And the second, the 2 1 element will be nx h cot by 2 plus I ny h cot by 2. And the second 2 2 element will be minus nz h cot by 2. So now you need to find out the eigenvalue of this matrix equation. So for any matrix, you can find out the eigenvalue by equating the determinant equal to 0 by taking determinant of n dot s minus lambda equal to 0. So this is how you can find out the eigenvalue. Now, if you put if you solve this matrix, what you will get is you will get the eigenvalue lambda, which is equal to plus or minus h cot by 2. So The result of this experiment will be plus or minus h squared by 2. Okay. So in any arbitrary direction, if you calculate what is the spin of this particle, then you will get a value either plus h squared by 2 and minus h squared by 2. So the answer will be in option D. So D will be the answer to this problem. So let us go to the next problem. So please read out the question. Please go through the question once. I am not able to see my tab. Please let me try again. In the meantime, please go through the next problem. So the next problem, it's still the same. I'm not able to connect my tab. So let me show how you can proceed the next problem. So next problem is in a basis in which the z component z of the spin is diagonal. An electron is in a spin state psi equal to 1 plus I by root 6 and root over of 2 by 3. Now it is asking the probability that a measurement of Sz will yield the values h cut by 2 and minus h cut by 2. Okay, so the spin state is given. Now it is asking if you do a measurement Sz, then what will be the probability of getting h squared by 2 and minus h squared by 2. So for that, what you can do is you need to express this psi, the state, the spin set psi in terms of the eigenvector of Sz. So Sz, you know, Sz is the matrix element of Sz is given by this equation, which is h squared by 2, 0 minus h squared by 2, 0, 0 and minus h squared by 2. So you see that it is a diagonal matrix. That means the eigenvalues of this matrix will be the diagonal elements, which is h squared by 2 and minus h squared by 2. Now, if you use this eigenvalues and if you calculate the eigenvectors that you got is 1, 0 for the eigenvalue h squared by 2 and 0, 1 for the uh, eigenvalue minus h squared by 2. Okay, so now you can write psi in terms of this. So 1, 0 you can represent it as a ket with a up arrow, and 0, 1 you can represent it as a ket with this with a symbol down arrow. Okay, so now using this eigenvectors of Hz, what you need to do, you express the spin set psi in terms of this up arrow and down arrow. So psi is already given to you. So psi now you can represent the psi as this, which is 1 plus I root over 6, 1, 0 and 1 minute. In not able to show the pointer also. Browse my computer. Set it. No, not taking. Let me set the windows only. So now you can write it in terms of this upstate and downstate. So now the probability that the measurement will give h squared by 2 will be the equal to the probability of getting the eigenstate that is correspond to the eigenvalue h squared by 2. So for h squared by 2, the eigenstate is 1, 0. That means upstate, and so the probability will be according to the quantum mechanics postulate. It will be equal to square of the inner product of this upstate with psi square divided by psi. So now if you take if you check whether psi is normalized or not, then you will find out that psi inner product will be 1. So that means psi is normalized. Okay. So psi is normalized, so probability of getting h squared by 2 will be equal to square of the inner product of obstate with psi. So that means it will be equal to square of the coefficient that is near to the that is adjacent to the obstate, which is 1 plus I by root 6. Okay. So that means the probability of getting h squared by 2 is nothing but equal to 1 by 3. Similarly, if you want to find out what is the probability of getting minus h squared by 2, so this will be equal to this is nothing but getting the eigenstate, which is downstate, which is eigenvalue minus h squared by 2. So the probability will be the inner square of the inner product of downstate with psi square. So you see that coefficient that is correspond to this downside is root over 2 by 3. So the probability will be 2 by 3. So the probability of getting h squared by 2 is 1 by 3 and the probability of getting minus h squared by 2 is 2 by 3. So the answer will be D. Okay. So let us move to the next question. Please go through the question once. So the next problem um, is easy problem. So it is based on the spherical harmonics. So let me read out the question for you. It is telling yxi equal to 1 by root 2 y22 minus y2 minus 2, where ylm are the spherical harmonics. Then which of the following is true? Yxi is an eigenfunction of both L square and Lz. Yxi is an eigenfunction of L square but not Lz. The third option is yxi is an eigenfunction of Lz but not L square. And the last one is yxi is not an eigenfunction of either L square and Lz. Okay, I forget to write L square and Lz in the D option. So, so if you see yxi, then it is 1 by root 2 y22 and minus y2 minus 2. So in the first term, if you see, if you find out the what is the L and M value for this spherical harmonics, then you will get L equal to 2 and M equal to 2. Now in the second y2 minus 2, L is equal to 2 but M equal to minus 2. Now, if you compare these two terms, what you will see, the L value is same in both terms, but the M value is different. So, L is the eigenvalue for L square operator and M is the eigenvalue for Lz operator. And you see that M is different, but L is same. So, that means this superposed state Yxi, it will be a eigenstate for L square operator because they have same because the state that makes this superposed state have same L value, but it will not be a eigenstate for the Lz operator because the M value is different. So this is one of the short question. It's one of the easiest question that you can solve. So let us go to the next question. So the next question, before solving the next question, please go through it once. Still, I'm not able to connect my tab. Okay, so let me solve all the problems in this manner also, in this manner, because I'm not able to connect my tab. Okay, so the next problem is for a 1D harmonic oscillator, calculate the expectation value of energy and the time evolution of the expectation value of the coordinate and momentum, provided that in the initial state t equal to 0, it was in the state described by the following Kate vector, which is alpha equal to 1 by root 2, 31 Kate plus 32 Kate, where n, the Kate n are the Kate vectors of the stationary state. So it is asking, so a state is given to you, the state of the particle in a 1D harmonic potential, which is alpha equal to 1 by root 2, the Kate 31 plus Kate 32. Now it is asking about what, in the first one, it is asking about what is the expectation value of energy. So expectation value of energy is easy. You need to solve you need to use the postulates of quantum mechanics. So for energy expectation, what you need to calculate? The expectation of alpha h alpha and divided by alpha. So alpha is, if you check, alpha is normalized. So that means the expectation value of E is nothing but alpha h alpha. So the expectation value, you can also write it as the summation of energy eigenvalue with its probability, right? So the probability, so what kind of state you have here? You have the state 31 and another state 32. So that means the energy states are 31, 32, and its energy eigenvalue for the state 31 will be 31 plus half h cut omega, and for 32 state will be 32 plus half h cut omega. And you see that in alpha, these two states have the coefficient 1 by root 2.
So that means the probability of getting the Kate 31 will be square of 1 by root 2, which is half, and the probability of getting the Kate 32 will be square of 1 by root 2 will be 1 by 2. So both state have equal probability, which is both state have probability of 50-50. Now, if you put the energy eigenvalue and the probability, then what you will get is the expectation of the energy eigenvalue is 32 h got omega. So the answer to the problem 1 is 32 h got omega. Okay. Now let us see the next problem. So next is it is asking about what is the time evolution of this expectation value of the coordinate and momentum when the ket is alpha. Now you know that yeah, in the introductory part, I have shown you that the position operator it changes with time according to equation 3 here. So the time evolution of this position you can write it as x0 cos omega t minus p0 by m omega sin omega t. Similarly, for the momentum operator, the time evolution you can write it as p0 cos omega t minus m omega x0 sin omega t. So now, if you want to find out what is the expectation of this position operator with respect to time, what you need to take is you need to take the expectation of this equation 3, which you can write it as the expression which is given in the fifth equation. So that means the expectation of the position operator is the expectation of x0 multiplied by cos omega t minus the expectation of p0 multiplied by sin omega t by m omega. Okay. So you see that the expectation of the time evolution of xt depends on in the expression of x. So x expression, you know that it is the root over of h cut by 2 omega a plus a dagger. So if you take this root over of h cut omega h cut by m omega is So it will give root over of 32 with the get 32. So that means you will get the expectation of x0 is 4x0. Okay. Now um, for the expectation of momentum operator, what you can do, you use the expression of use the ladder representation of the momentum operators. So similar to the position operator, you need to use the ladder operator representation of the momentum operator, which is given in this bracket, which is p equal to I root over of m h equal to omega by 2 a dagger minus a. Okay. So now similar to the position representation, so what you can do is you put the expression for the ladder operator in this expectation value and solve it and take those terms for which the values are non-zero. Okay, so if you if you solve it, then you will see that only the terms like 31a 32 will be non-zero and 32 a dagger 31 will be non-zero. Okay, if you take other terms, then it will be 0. Now, when a acts on 32, then it will give root over of 32 and negate 31. So that means the first term will give minus of root over of 32, and for the second term, it will give a dagger acts on 31, so it will give root over of 32 and negate 32. Now, if you compare these two terms, then you will see that they will cancel each other. So that means the expectation of the momentum operator at time t equal to 0 is 0. Okay. So now if you see equation 5, so the second term will be 0, only the first term will remain, and you already calculate the expectation of x0, which is 4x0. So that means the time evolution of the position operator, it will be 4x0 cos omega t. Okay, this is how you can calculate the time evolution of a expectation value of position. Now, if you see, if you calculate the second part, like the expectation of the momentum operator, so it will be given by, if you see, it will be given by the fourth equation. So it will be equal to expectation of as shown in this, it will be px0 cos omega t minus m omega expectation of x0 sin omega t. Now you already calculate the expectation of momentum at time t equal to 0, which is 0. So this means the first term will be 0, only the second term will remain. So the second term, in second term, you see there is a expectation of position operator here at time t equal to 0, which we have already calculated, and it is 4x0. So that means the time evolution of the momentum operator will be minus 4 m omega x0 sin omega t. Okay, so that means the answer will be the time evolution of the position operator will be 4x0 cos omega t, and the time evolution of the expectation of momentum operator will be minus 4 m omega x0 sin omega t. Okay. This is how you can calculate the expectation value time and its time evolution. So let us go to the next question, which is question number 8. So go through the question once. Go through the question number 8. So let me read out the question for you. So it is, consider a harmonic oscillator in the state psi, which is equal to e to power minus alpha square by 2 multiplied by e to power alpha a dagger on a state 0, where the kate 0 is the ground state, a dagger is the raising operator, and alpha is the complex number. Now, what is the probability that the harmonic oscillator is in the nth eigenstate, which is K10? Okay. So, a state is already given to you. Now, they are asking about what is the probability that you will find the particle in the Kate n. So, let's see whether, so probability you can easily find out by using the postulates of quantum mechanics. So, probability of getting a state n will be the inner product of n with psi square divided by psi psi. So first, check whether psi is normalized or not. So for that, you can check it like psi is already given, which is e to power minus alpha square by 2, e to power alpha a dagger 0. Now you know that the expansion for the e to power x is nothing but summation of n equal to 0 to infinity x to power n by n factorial, right? So that means if you expand this second term e to power alpha a dagger, so you will get this expression, which is summation of n alpha a dagger to power n factorial 0. Okay. So now what you have to do is, you know that the state. So if you recall this expression for the kate n. So the kate n is nothing but 1 by root over of n factorial a dagger to power n acting on a kate 0. So if you act n times, if you act the raising operator n times on the ground state, then you will get the kate n. So from this expression you will get, if you see the right hand side, you will get the expression for a dagger to where n acting on its kate 0 is nothing but root over of n factorial acting on a kate n. So now if you use this equation 6, then you will and solve the expression for psi, then what you will get is, the psi is written as e to power minus alpha square by 2 summation of n alpha to power n root over of n factorial n divided by n factorial. Okay. Now for this, if you want to check whether psi is normalized not, so you need to find out whether psi equal to 1. So psi is already given, the kate psi, you need to find out what is the bra corresponding to this. So now if you put the bra corresponding to this psi, then what you will get, the psi will be given by e to power minus alpha square summation of n alpha star alpha to power n root over of n factorial square divided by n factorial square and the inner product of n. And this inner product of, in this summation, the summation is over all n, like n can be 1, 2, 3, 4. So this summation will be non-zero. This summation will give a non-zero value whenever the n are same. So whenever the n, let's say if you are calculating for n equal to 2, then only the 2 to inner product will be non-zero and other terms are 0. So that means you will get the value psi equal to e to power alpha square summation of alpha to power n and divided by n factorial. Now the summation of n alpha to power n by n factorial is nothing but e to power alpha square, right? So the psi will be equal to 1, and so the psi will be normalized. there will be a 2 in the terms. I forgot, I mistakenly write it as n, but the summation will be, the term will be alpha toward 2n. That's how you can got, there will be square here. Alpha square. Alpha star alpha will be alpha square, right? So this is not alpha, this is alpha square. So you see that psi is normalized. Now you checked psi is normalized. So to find out the probability, you have to take the inner product of n with psi to the power whole square. So psi is given. So now you have to just take the inner product of n with psi, which is given by e to power minus alpha square by 2 summation of n alpha to power n by root over of n factorial and the inner product of n. So the final expression will be given by this form. The last equation, which is e to power minus alpha square by 2 alpha to power n divided by root over of n factorial. So the now if you calculate the n psi square, the inner product of n with psi square, then this is nothing but e to power minus alpha square alpha to power 2n by n factorial. So that means you got the probability. So probability is nothing but the inner product of n with psi whole to power square. So the probability is e to power minus alpha square into alpha to power 2n by n factorial. So the answer will be A, which is e to power minus alpha square alpha to power 2n by n factorial. So let us go to the next problem. Please go through the question once. So let me read out the question for you. So it is telling a spin half particle is in a state 1 by root 2 kate up arrow and plus kate down arrow. Okay, so where kate up is and kate down are the eigenstate of SZ operator. Now it is asking the expectation value of spin angular momentum measured along the x direction is. So the state is given, the state of the particle. Now you are making a measurement of spin angular momentum along x direction, that is Sx. So now it is telling that if you do this kind of measurement, then what will be the outcome? So for that, what you have to do, you have to express the state that is given to you in terms of the eigenvector of the measurement, the operator that you are taking to do the measurement, which is Sx. So size given, so up and down are the eigenstate of Sz operator. So up means the state 1 0, the column vector 1 0 for eigenvalue h squared by 2, and down means the column vector 0 1 for eigenvalue minus h squared by 2. So if you now put the value matrix representation of this up and down state, then you will get psi will be given by this last equation which is equal to 1 by root 2, 1 0 plus 0 1. So it will be, so psi in terms of the column vector, you can write it as 1 by a column vector, which have a element 1 by root 2 and 1 by root 2. So now if you are taking a measurement Sx, so Sx, you know, it is given, it is written in terms of the Pauli matrix as h cot by 2 sigma x. So sigma x 0 0 1 1 0. So now, so if you need to find, if you want to find out the what is the matrix representation of Sx, then it is given by h cot by 2 0 1 and 1 0. So, so the question is asking about what is the expectation of this spin angular momentum along this x direction. So use the postulates of quantum mechanics, which is the expectation of Sx equal to psi Sx psi divided by psi. So psi is normalized because you see the coefficients are 1 by root 2 and 1 by root 2. So it is normalized. So now you put, so the denominator will be 1, but the numerator, what you have to do is you have to put the matrix element of psi, Sx and psi. So the column vector, you know, you can then column vector of psi, you know, from that you can find out the bra vector of psi, which is the row vector 1 by root 2, 1 by root 2. So now use this column representation and use this matrix representation of xx and psi and solve this matrix equation. So if you solve it, then you will get that the expectation of Sx will be h cot by 2. So the answer you will get is h cot by 2, which is answer D. So let us go to the next problem. Please go through the problems once. So let me read out the question for you. So it is telling, consider the Hamiltonian H, which is given by minus EB by MC SZ. And EB by MC, you can write it as omega. So the H Hamiltonian is minus omega SZ. So now it is asking, write the Heisenberg equation of motion for the time-dependent operator Sx, Sy, and Sz. So it's a simple question. You need to use the Heisenberg equation and you need to calculate the commutation relation, because in Heisenberg equation there are commutation relation. So if you see the last equation that I have wrote, it is if you need to find out the Heisenberg equation for the Sx, then it is given by dSs by dt equal to 1 by IH cot commutation of Sx with H plus the expectation of dou Ss by dou T. Now, if the spin angular momentum along the x, if the it doesn't depend on time explicitly, then the second term will be 0. So what then you are left with finding out the commutation relation of Sx with H. So H is already given to you, which is minus omega Sz. Okay, there is a there will be a minus here. So if you put minus omega SZ, then you will get minus omega by IH cot commutation of Sx with Sz. So commutation relation of Sx with Sz you already know, it is IH cot. So similar to the orbital angular momentum Lx Ly Sz commutation relation, the spin angular momentum also they also follow the same commutation relation. So the commutation of Sx with Sy will be IH cot, Sy with Sz will be IH cot, and there will be a operator for X and Y commutation, it will be IH code SZ. For SY SZ, you will get IH code SX. And for Z, SZ and SX, then you will get IH code SY. So use the commutation relation, then you will find out that the Heisenberg equation for Sx will be omega Sy. So similarly, I think you can find out what is the Heisenberg equation for Sy and Sz. For Sy, you need to find out what is the commutation relation of Sy with Sz that you can get. And if you solve it, then you will get minus omega Sx. And for Sz, you can calculate the commutation relation of Sz with Sz, then but the commutation relation of Sz with Sz will be 0. So that means the Heisenberg equation for Sz will be 0. Okay, this is how you can calculate the Heisenberg equation. So let me keep this 11th question to my list next session because it's a long one. You can and it contains a lot of information. You can understand. You can use many concept to find out the answer. So it will help you to understand also many concept related to how you can go from one operator to another operator, how you can represent the operator in terms of a uh, outer product representation. So let me keep this question to for our next session. So let's solve one questions, which is the last one. So it is given a spin half particle uh, is in a uniform magnetic field has a energy eigenstate 1 and 2. So now the system is prepared in gate state 1, which is given by 1 by root 2, gate 1 plus gate 2 in time t. Now it is asking what is the minimum energy difference between these two levels. So here you are seeing there are two levels, right? 1 and 2. 1 and 2, there are gate 1 and gate 2. So now it is asking about, the state is already given. Now it is asking about the minimum energy difference between these two state 1 and 2. So what you can do is, so let me keep this problem. Okay, there are some information missing in the 11th, the 12th question also. So let me keep this question for the next session because I think there is some information missing in the question. So let me correct, then let me put the additional information and let me solve it in the next session. Okay, so uh, thank you all for joining this section. So I hope this the problems that I have solved will help you understand the problems, not only the problems, also the concept that is related to the uh, quantum mechanics, and that will also help you to solve the daily assignment. So I hope the problems that I have solved today is understandable to you. And if you have any problems, then you can ask me in the discussion forum. And thank you all for joining the section. So let's meet on the next Saturday. So for now, thank you all. Bye.